So integration by substitution, we usually call it U-Substitution, and it's like the chain rule. Where we have a composite function or a function inside of a function. So let's look at one that we've done something similar before. If I want to find the integral of 5e to the 5x dx, then my inside for my composite function would be 5x. We know the antiderivative and the derivative of e to the x, but when it's a 5x, it's more complicated. That would be a chain rule or a composite function. And the outside of my function is e to the something. And the 5 in front here is just a constant. We know we keep the constant there. So logically, when I find the antiderivative of this thing, I keep the 5 out front. The antiderivative of e to the something is e to that something. But we know if we take the derivative of e to the 5x, we would chain rule that problem. It would bring a 5 out front. And so we need a 1/5 to deal with that. And then we're going to put a plus c on it. Okay, so what this turns into, 5 times 1/5 goes to 1. I get e to the 5x plus c. So we check that, right? If I take the derivative of e to the 5x, we would get e to the 5x times the derivative of the inside function would give me a 5. And the derivative of the c would be 0. So I see this matches my integrand. Okay, so that was the logical way to figure it out. These are going to be more complicated than this one. This one I can figure out pretty well just by knowing something about the antiderivative and then playing with what its derivative is to make it match up. If we were to use U-substitution on it, we're going to pick u to be the inside function. Now, that means I'm going to rewrite this whole integral in terms of u instead of in terms of x. So I'm going to have to replace the dx as well, because we're going to now integrate with respect to u. So I take the derivative of my u equals 5x, and I get du dx equals 5. It doesn't look very much like a u. And we talked briefly about how we took a derivative and turned it into a differential equation that we could then integrate. We separated the variables and said that then du would be 5 dx if I multiplied both sides by dx. And what I'm trying to do here is solve for the dx so that I can replace it right there. So I can divide both sides by 5, and I'm going to get dx equals du over 5. It seems complicated right now, but you'll get the hang of it. So my integral becomes the integral of 5 e to the u, because I replaced my 5x with a u, And then I'm going to replace my dx with a du over 5. And now my 5 divided by 5 will go to 1. So my integral is e to the u du, and that looks just like our e to the something. The antiderivative of e to the u is e to the u, so we're going to get e to the u plus c. But we started in terms of x, we want to go back to being in terms of x. So we back substitute the 5x in for the u, and we get e to the 5x plus c, the same thing we got before. So this demonstrates the procedure of U-substitution, but it's on a pretty easy one. Let's try one that's a little bit more complicated. Right. Find the integral of the quantity x squared plus 1 squared times 2x dx. Without U-substitution, I would have to multiply out that binomial, distribute the 2x, and power rule the whole thing. That's a lot of algebra. Instead, I can do a U-substitution, and these are going to kind of be a guess and check thing. The u that you pick might not always work out, in which case you try something different. The guideline I'll give you to pick a u is to pick something complicated, but not the most complicated thing in the integrand. So if I look at this one, I see 2x, that's pretty simple. X squared plus 1 all squared, that would be the most complicated thing in here. So a little bit less complicated than that would just be the x squared plus 1. And with some practice with these, you're going to start to see the du in the problem that'll make these things work. So if I pick u equals x squared plus 1, then du would be 2x. And this would be du dx, right? But I'm going to go ahead and move that dx over when I do these. So whenever you find your du, just put your dx on the other side. Do you see the du in the problem now? There's my du, and I see it right there. That's going to cancel out nicely.
When you choose your
Okay, now I see the du in this problem, but some students like to go step-by-step procedural every time, so let's do that. Let's divide both sides of this by 2x so that we're solving for the dx. So in this case, I get dx equals du over 2x. Now I'm going to go back to my problem and rewrite it all in terms of u. So my x squared plus 1 becomes a u, and it is squared. Then I have times 2x, and then I'm going to replace my dx with du over 2x. Those simplify, and this is now the integral of u squared du. Everything's in terms of u. I can find the antiderivative using the power rule. So I have a u squared that becomes a u to the what? it's going to become u cubed, which means we put 1/3 in front, and I'm going to back substitute my u in there. So this would be 1/3 u cubed, but u is x squared plus 1, and then we need plus c.
That would be your answer.
Mm-hmm.
So wait, since
All right, slight variation of the last problem. Not everything is always going to simplify, cancel out beautifully with the dx. But that's okay as long as the x's get removed from the problem. Okay, so the last problem had 2x in it. This one's just got an x. I'm going to pick the same u. U equals x squared plus 1. Then my du equals 2x dx. If I solve for my dx, we're going to get du over 2x equals dx. And when I rewrite my integral, I've got the integral of x times the x squared plus 1 will become u, and that'll be squared. My dx is replaced with a du over 2x. My x's will cancel, but the 2 will not. So that just means we have the integral of 1/2 u squared du. That's still doable. So there's not always going to be exactly the du in the problem, but as long as we can take everything that's an x and turn it into terms of u, it's working. So the antiderivative of this, we keep the 1/2 out front. We get u cubed, which means we get a 1/3 out front. Back substitute the u, which is x squared plus 1, and we get a plus c. And if I multiply my coefficients together, now I have 1/6 x squared plus 1 cubed plus c.
someone's still looking at on.
Dude, I'm gonna be 30. I'm still gonna be training with this stuff. So I'm not gonna be a math major.
Okay, so when I look at this problem, I see a composite function. If it was just x to the 1/2, I could integrate it, right? But we have something other than x on the inside here. And in this problem, there's very few choices for me to pick my u. So we're going to pick it as the inside. So if u is 2x minus 1, this problem's going to turn into a u to the 1/2 that I can power rule, correct? But du is 2 dx. But I don't see 2 in front of the dx up here. So if we divide both sides by 2, then I'll replace the dx with a du over 2. So my problem becomes the integral of u to the 1/2 times, I'm replacing my dx with a du over 2. Dividing by 2 is the same thing as multiplying by 1/2, right? So I'll bring that 1/2 out front, just so I see it as a constant at the front of the problem. So then we take the antiderivative, I keep the 1/2, u to the 1/2 becomes u to the what? to the 3 over 2, which means I put what in front of it? 2 over 3. I'll back substitute my u in there, which is 2x minus 1. And I need a plus c. And then we clean it up. We multiply our coefficients together. 1/2 times 2/3. Well, 2 over 2 goes to 1. We're just going to get 1/3. 2x minus 1 to the 3/2 plus c.
I want to do that. Is choosing the 2x as your u?
Let's look at a variation of what we just did. Where everything doesn't cancel out so beautifully. All right, I'm going to pick the same u as I did in the last example. U equals 2x minus 1. Then du equals 2 dx. And so we're going to get du over 2 for our dx. When I rewrite this integral, I can replace the 2x minus 1 with a u, and that'll be raised to the 1/2 power. My dx is du over 2. So I still have an x in this problem, mixed in with my u's. And our goal is to have everything be in terms of u. So what I can do is I can solve that right there for x. So I would get, add 1 to both sides, u plus 1 equals 2x. Divide both sides by 2. And we've got x equals u plus 1 over 2. Let's see what happens if we put this into our integral. So my integral becomes u plus 1 over 2 times u to the 1/2 times du over 2. Now, in order to be able to manipulate this thing, I want to clean it up a little bit. I want to make it look a little bit easier to integrate. I want to see power rules. So what I see here is I have a 1/2 times another 1/2.
So it's going to be a 1/4.
So that's a 1/4, and I'm just going to put that out here in front of the problem so I don't even have to look at it. Then this becomes similar to what we were doing before. I need to distribute the u to the 1/2, but then it's just going to be a power rule problem. So u to the 1 times u to the 1/2 is u to the 3/2 plus 1 times u to the 1/2 is u to the 1/2. And now we can integrate. So what I'm going to do is I'm going to keep that 1/4 in front of everything. U to the 3/2 becomes u to the what? 5/2, which means 2 over 5 comes out front. I back substitute for my u. And then u to the 1/2 becomes u to the 3/2, so I get a 2/3 out front, and I back substitute. And then we just need to clean that up. So I'm going to multiply my 1/4 by 2/5. And that'll be, what, 1/10 times 2x minus 1 to the 5/2 plus 1/4 times 2/3 thirds will be 1/6 times 2x minus 1 to the 3 halves plus c.